Hello everyone, welcome back to CMPT 459 Data Mining. This is the second part of the section Clustering. In the first part, we introduce the concept of clustering and discuss the partitioning methods, including k-means and k-methods. In this part, we'll focus on hierarchical clustering methods. Hierarchy is an agreement or classification of things according to inclusiveness. Organizing things into hierarchies, indeed, has been a long time method for human beings to understand the environment, the nature, and organize their knowledge. For example, in biology, there are many different species. The construction of biology essentially is the process of the construction of the hierarchy of those species. Hierarchy is a natural way of abstraction, summarization, completion, and simplification for understanding. Typically, we do not assume substantial supervision in building hierarchies. In other words, building hierarchy itself is an exploration process. We try to organize a given set of objects into groups and subgroups. There is some heuristic quality guidance on the quality of hierarchy. To build hierarchy, essentially, we are trying to group data objects into trees of clusters. For example, here, we can see that this is the set of all objects. Then we have different subsets at different levels, and each subset may be further partitioned into smaller subsets. At the leaf node, or at the lowest level, we have all the clusters of very small size, or to the extreme case, a cluster has only one object. Therefore, a hierarchy essentially is a tree of clusters. Obviously, to build such a tree of clusters, we have two alternative ways. First, we can do the top-down approach. At the very beginning, we can put all the objects into one cluster, and then we keep partitioning large clusters into smaller ones until we reach the lowest level where either each cluster has only one object or each cluster is small enough. So this is the top-down approach. Alternatively, we can do in a bottom-up approach. We start with clusters where each cluster has only one object. Then we keep merging small clusters into larger ones. The merge process continues until all the objects are merged into one big cluster. That's the root of the tree of clusters. This is the bottom-up approach. Agonies is a bottom-up approach. Agonies stands for agglomerative nesting. Initially, we put every object into a cluster, and then we conduct step-by-step merging of smaller clusters into larger clusters. This iteration continues until all objects are put into one big cluster, which is the root of the tree of clusters. In Agnes, we have the single link approach. Each cluster is represented by all of the objects in the cluster. The similarity between two clusters is measured by the similarity of the closest pairs of objects belonging to different clusters. Once we build a tree of clusters, we will have this dendrogram. Dendrogram shows how to merge clusters hierarchically from bottom up. Of course, we can also look at dendrogram as a top-down tree. In this case, it shows how we can decompose data objects into multi-level nested partitioning. Once we have the dendrogram, we can cut the dendrogram at some level to form a clustering, because we mentioned that a clustering is a set of clusters that partition the set of objects. Once we cut a dendrogram, then each connected component in this tree becomes a cluster. Diana is a top-down approach. Diana is for divisive analysis. The idea of Diana works as follows. At the very beginning, all objects are put into one cluster. Then we conduct a step-by-step splitting of those large clusters into smaller ones until each cluster contains only one object. For example, here at the very beginning, we put all the objects into one cluster, and then we partition the objects into two clusters here. And in the next step, next iteration, we can further partition a larger clusters into smaller ones, a larger cluster into smaller ones. And this partitioning process can continue iteratively until each cluster contains only one object. Now, one important issue is how we can measure the distance or the similarity between two clusters. There are different approaches we may consider. For example, we may use the minimum distance. Essentially is that we have two clusters, I and J, Ci and Cj. We try every pair of objects, one from Ci and one from Cj. We use the shortest distance between those pairs as the distance between the two clusters. In this way, essentially is that we try to use the closest pairs of objects in the two clusters to represent their similarity or distance. Alternatively, we may use the maximum distance, which is indeed the farthest pair of objects from the two clusters. For the Ci and Cj, we pick one object from Ci, another object from Cj, and we try to find the maximum distance between such pairs and use that maximum distance as the measurement of the similarity. Or we can do the mean, or the mean essentially is that we can calculate the mean of Ci and the mean of Cj, and then we use the distance between their means as their distance. Or we can do the average distance, meaning we have Ci and Cj for every pair of objects between Ci and Cj, meaning you pick one object from Ci, one object from Cj, we calculate the distance between these two objects, and then we sum up all the possible pairs and then get the average. Please note that mean distance and average distance here are different. They are calculated in completely different ways. The challenge of hierarchical clustering is that it is hard to choose good merge or split points. And also, when we do the hierarchical clustering, once we make a decision to merge or split clusters, we never undo the merge or splitting. Therefore, the merging or splitting decisions are very critical. And also, the hierarchical clustering algorithms we introduced so far have high time complexity. The high time complexity is in the order of quadratic, because for any object n, we need to calculate the distance between the object with the other objects in order to find the ones that we should combine. Therefore, essentially, we need n-square computation operations. That comes to the quadratic time complexity. In order to improve the efficiency and effectiveness of hierarchical clustering methods, one idea is that we can integrate hierarchical clustering with some other techniques. There are some other methods introduced, such as Birch, Cure, Chamberlain, and Rock. In this course, we will use Birch as an example to explain. Birch is for balanced, iterative reducing and clustering using hierarchies. The central data structure in Birch is a clustering feature tree, which is a hierarchical data structure to summarize object information. In Birch, clustering the object is reduced to the problem of clustering leaf nodes of the CF tree, the clustering feature tree. So let's first explain what clustering features are. For each cluster, we can form a clustering feature vector. The vector is very simple. It contains three different components. One is n, the number of data points. The second is ls, which is the sum of the vectors of those points assigned to this cluster. And ss is the sum of square of those objects assigned to this cluster. So, for example, here we have one cluster, and those are the values of the points assigned to the cluster. And then the CF, the cluster feature, is 5 because in total we have 5 different objects. And then we have 1630 because we have the sum of those points. And 3 plus 2 plus 4 plus 4 plus 3 is 16. And 4 plus 4 plus 5 plus 7 plus 8 is 30. And similarly, we can calculate the square sum of those vectors, which gives 54 and 190. The CF tree in Birch has the following properties. It uses the clustering feature, which summarizes the statistics of a cluster. There are many cluster quality measures can be derived from the clustering feature. For example, the radius and the distance can be easily derived from the clustering feature. And also, the clustering features have a very nice additivity, meaning if I have two clusters cluster 1 having clustering feature CF1 and cluster 2 having cluster feature CF2. Then, to form the clustering feature of the combined cluster, I don't really need to go back to the individual objects in this cluster. Instead, I can simply get the sum of the corresponding components of the clustering feature, because the sum of the number of objects in the cluster is the sum of those numbers in each subcluster. And so for the L1 and SS components. Therefore, the task of clustering becomes how to build a clustering feature tree. We want to have a height-balanced tree storing the clustering features for hierarchical clustering. Here in the CF tree, a non-leaf node has descendants or children as the subclusters, and the non-leaf nodes would store sums of the clustering features of the children. This is an example of the CF tree. We have different clustering features and we have children, and then for a non-leaf node, we have further pointers to children's and further clustering features. In a CF tree, the parameters include the branching factor, which is the maximum number of children that this node can hold. And also, the CF tree carries a threshold, which is the maximum diameter of subclusters stored at the leaf nodes. Therefore, we can use the threshold to decide whether we want to split one cluster into subclusters and thus span the tree. The Birch clustering algorithm works as following steps. In the first phase, we scan the database once to build an initial in-memory clustering feature tree. And this tree is a multi-level complexion of data that tries to preserve the inherent clustering structure of the data. Then, in the second phase, we can use an arbitrary clustering algorithm to further cluster the leaf nodes of the CF tree. Essentially, we can use the CF tree as a summarization of the data, and then we can use other clustering algorithms to build better clustering based on the CF tree information. We won't go into the detailed steps in the Birch algorithm. If you are interested, please refer to the corresponding literature. Birch has some very nice advantage. First, Birch is linear with respect to the dataset size. In other words, because Birch only scanned the dataset once to construct such a tree and summarize the dataset, it has a very nice clustering performance. Indeed, Birch was proposed even before the term of data stream was proposed. Therefore, Birch can be regarded as one of the earliest streaming algorithms. If you have more time and more resource to scan the database multiple times, you can employ those further scans to improve the quality of the clustering. Birch also comes with some limitations. First, Birch can only handle numeric data, and it is not capable of handling categorical data, for example. And also, Birch is sensitive to the order of data records. If the data is fit into the Birch algorithms in different orders, the cluster feature tree output would also be different. That's one drawback of Birch. In this part, we introduce the idea of hierarchical clustering. Using two examples, we illustrate the alternatives of constructing hierarchies, the top-down approach and the bottom-up approach. Last, we introduce Birch, a streaming clustering algorithm that uses linear time to summarize a dataset and form the hierarchy. That's all for the hierarchical clustering. Thank you, and see you next time. Bye-bye.